So we're going to do a little bit of review on the material that we talked about last time, although I'll kind of add a few things in here as we go, since I didn't mention that the rule for determining whether something that is in a mechanism but not in the overall reaction can be determined, it might either be a catalyst or an intermediate, right? So a catalyst is involved in the mechanism, otherwise it could not speed up the reaction, but does not appear in the overall reaction, right? It is consumed at the beginning of the reaction and then is regenerated somewhere else, right? So the concentration of the catalyst doesn't change, right? It stays the same through the entire reaction. An intermediate is generated somewhere as a product in the mechanism, but then gets consumed by something else, and so it also does not appear in the balanced chemical equation, right? So in a mechanism, in a multi-step mechanism, you can tell whether something's a catalyst or not, whether it appears first on the left-hand side, right? If you're starting with the first elementary process, if there's something on the left-hand side that doesn't appear in the balanced reaction, right, then it's going to be a catalyst. Even if it's the second one, although this is unlikely. In the second, but not impossible. In the second elementary process, if something first appears on the left-hand side but it's not in the balanced reaction, it is a catalyst. So anything that's on the left-hand side first is a catalyst. Anything that's on the right-hand side in first is an intermediate. All right, so problem number 11, we haven't done this one. Molybdenum plus nitrogen goes to form molybdenum. Molybdenum oxide goes to form molybdenum in the elemental state plus N2O. The activation energy and overall delta E are 471 and 430, right? So that means the activation energy is 471, and then the energetics, the fact that that's positive means what? Endothermic. All right, so what does that mean about the reactants compared to the products? The reactants are lower than the products, right? So whenever you see a problem like this, right, so it says determine the activation for the reverse reaction, right? So we are going to see in the next chapter that most chemical reactions reach an equilibrium where the forward reaction initially goes, and then at some point as the products build up, right, then the reaction is going to start going in the reverse direction. So we haven't talked about equilibrium yet, but there will be an activation energy associated with both a forward reaction and a reverse reaction. So we have this kind of diagram right there. All right. And so when you're asked for when you see a problem like this, I would recommend you draw the diagram. In my opinion, it makes it much simpler. All right, so here we're talking about we're given information for the forward reaction, right? So that distance right there is the activation energy, and this distance right there is the delta E, all right, which is given as 430 for this, and then 471 for that. Okay, so then the question that's being asked is, what is the activation energy in the reverse direction? In other words, if you start up here, you have to go over the hump and then form products, right? That distance right there is the activation energy for the reverse reaction. This is activation energy for the forward reaction. All right, so what is the activation energy for the reverse direction? Okay, it'd be 471 minus 430. All right, so that's what, 41 kilojoules per mole. All right, so if you visually, you can see that this plus this equals that. And so if you want this unknown right here, you have to take this distance and subtract off, or that quantity, subtract off that quantity, and that leaves you with that one. All right, so if you ever get a problem that looks like this, I recommend you draw a diagram. I mean, if you can do it in your head, that's fine, but you can make sure you do it right if you draw the little diagram like that. All right, and that is a learning objective. Sketch a potential energy profile showing the activation energies for the forward and reverse reaction. All right. Now, it says, how would this be affected by a catalyst? If there were a catalyst in this chemical reaction, what would that look like? Yes?
It would lower the activation energy required.
Okay, so it might look like that. Right. So there, that lowers the activation energy there, and it lowers the activation energy there. Now, how much did it lower the forward reaction compared to the reverse? This is for something in the next chapter. If we make a note of this in our mind, it'll make something in the next chapter make more sense. Mr. Ventola?
Since the forward reaction has a higher activation energy, it's going to be at a lower percentage.
That's true. It is a lower percentage, but I want to talk about the absolute amount. How much did it lower the forward reaction compared to the reverse reaction?
The same.
Exactly the same. Okay? And that's going to be important when we talk about how a catalyst will affect equilibrium. Right? So since it lowered the activation energy the same, then what that means is it doesn't affect the equilibrium. So since the rates are increased in both directions by the same amount, or the relatively same amount. All right, so next, shown below is a two-step mechanism for the production of NOBr. What is the net chemical reaction? All right. Again, this is a learning objective. If you're given a mechanism, you've got to figure out what the reaction is. And then identify any intermediates. All right. Anybody know how we would figure out which reaction this is?
Cross out the intermediates.
Yep, cross out the intermediates. And if there were a catalyst in there, we'd be crossing out catalyst too. So anything that appears on both sides. All right, so this one is actually fairly straightforward. 2NO plus Br2 goes to form 2NOBr. All right, and the intermediate is NOBr2. Okay, here's a multi-step mechanism, 4 different steps. It says, what is the net chemical equation here? Anybody come up with what that net chemical equation is?
H2 plus 2ICl.
Plus 2ICl goes to form
2HCl plus I2.
Okay, let's check that. So the H atoms cancel, the HCl cancels, the I atoms cancel there. So we've got 2ICl plus H2 goes to form 2HCl plus I2. Yes, that is correct. Are there any intermediates in this mechanism? Are there any catalysts? Any catalysts here? Okay, no, there are no catalysts. There's nothing that appears first on the left-hand side. How many intermediates do we have? 3 of them. That is correct. So hydrogen is 1. Then iodine gas is another. And the HCl is another. So there are actually 3 intermediates.
You go over nothing, the whole catalyst. You said nothing.
Well, let's do the next example, and then I'll go over it, okay? Because I want to finish off the example so we can actually see something where a catalyst might be present. So the first 2, there are no catalysts. All right, so here is a 3-step mechanism. Okay? It says identify any intermediates, identify any catalysts. All right, so before you actually do that, what would you need to do? Or at least I would need to do this because I'd have to come up with the overall balance equation so I can compare and see if it's present in the balanced equation. Although you can still do the crossing out. And I guess you really don't need to do that. But all right, so that's how you get the overall one, is by crossing things out. All right, so what appears here is the silver 2+. Anything else? How about the thallium 2+?
Silver plus.
And the silver plus. Okay. So what's left is cerium 4 plus, 2 of them, plus a thallium 1 plus goes to form thallium 3 plus, plus 2 cerium 3 plus. Okay, are there intermediates here?
The silver 2 plus.
Okay, the silver 2 plus
Thallium 2 plus.
and the thallium 2 plus. Any catalysts?
The silver plus.
The silver plus. Okay?
How do you know it's catalyst?
Because it shows up first on the left-hand side. All right, so silver 2 plus shows up first on the right-hand side. Thallium 2 plus shows up first on the right-hand side. So that means it's an intermediate. The silver plus shows up first on the left-hand side. And so that means it's a catalyst. Okay, did that answer your question, Mr. Conrad? Okay. All right, so I briefly introduced the concept of temperature last time. How temperature affects reaction rates. And for most chemical reactions, as you increase the temperature, the rate goes up. For most chemical reactions, as temperature goes up, reaction rate goes up. And there are two reasons. There are two reasons. Anybody know why reactions would go up due to temperature? Yes?
More particles have more energy, so it takes less to go through the process of.
So it lowers the activation energy?
Yep.
No, that's not. I think you actually have the kind of idea, but that's not what actually causes it. Yeah.
As you increase the temperature, like molecules have enough energy to react.
To overcome the barrier. More molecules have the energy necessary to overcome the activation energy. Yes, that's one of the reasons, right? Because more molecules have the energy required to overcome the activation energy, E sub A. Right? So we talked about this on Tuesday. You have a Boltzmann distribution. So this is temperature 1. And as you increase the temperature, and that's temperature 2. And let's say that's the activation energy right there, E sub A. All right, so at the lower temperature, that many molecules have the necessary energy to overcome the barrier. But at the higher temperature, that many molecules have the necessary energy. All right, so this is speed, actually, and this is number of molecules. All right, so once you increase the temperature, more molecules have the higher kinetic energy necessary to overcome the barrier. Okay, anybody know what the second reason is? Yes?
Would be due to the increased solubility of the different chemicals?
Now that certainly would have an effect. So if something is more soluble at higher temperatures, and that thing that's being soluble is part of the reaction, then that certainly would be the effect. But I'm talking about any general. I mean, I'm not going to put that specific case because that's not always, that's actually, in most cases, not going to be the kind of reactions we're going to look at. Yes?
Since going through speed increases, collisions increase?
Yes, the number of collisions increase. Right. So more molecular collisions. Okay? So which one of those do you think has the greater effect? More collisions or more molecules having the energy greater than the... Yeah, all right. Pardon me?
First one?
That is correct. The first one is actually much more of an effect than the second one. Right? So if you increase, let's say you've got room temperature. Let's say around 200, well, let's just go 300 degrees. That's an easy number to work with. A little warm. 300 Kelvin. Right? Then you raise the temperature to 310, right, then for many chemical reactions, that will double the number of molecules that are past the activation energy. Okay, so a small 10-degree effect will increase the rate by twice. Okay, now the collisions, if you start at 300, then the number of collisions is directly proportional to the speed, and the speed is proportional to, let's see, temperature is proportional to 1/2 mv squared, so the velocity is proportional to the square root of the temperature. So if you want to, if you go from 300, what happens if you double the temperature? How much of an effect does that have? So that would be, how much would the velocity change if you went from 300 up to 600? Right? What would that ratio be under the temperature? Okay, 600 divided by 300, square root of 2. That would be a square root of 2, which would be a 40% increase. So you have to, the velocity would increase by 40%, right? So what that means is that at most you'd get a 40% increase by changing the temperature by 300 degrees, right? Whereas you get a 100% increase by only changing 10 degrees, because of this effect being a much greater effect than the collision. So normally for the collision part, we can basically ignore that, and the major effect is from the number of molecules that have to go over the barrier, increasing as you increase the temperature. All right, so there is actually a numerical expression that we can use called the Arrhenius Equation. Okay, and the Arrhenius Equation is related, is a relationship between the rate constant, right? We have a rate law that says rate is equal to K times the concentration of A to the X power, B to the Y power, the reactants raised to the powers, and K is how the is why an increase in the K is why reactions increase with increasing temperature. Right, so the rate constant increases. So it's equal to A e to the minus E sub A divided by RT. Right, that is the Arrhenius equation, one of the equations where K is the rate constant. In the rate law, A is something called a frequency factor, which actually depends on two things, which we'll talk in a second. E is the activation energy. Right, which we've talked about before, the barrier. R is the gas constant. And in this case, you're going to want to use 8.314. You've seen that before, right? The gas constant in terms of joules. And most of the time, we'd actually want to put that times 10 to the minus 3 so that it's in kilojoules per Kelvin mole. All right, so if you use 8.314 joules per Kelvin mole, activation energies are normally in kilojoules, right? So you report activation energies in kilojoules. So if you put that R in kilojoules, then you'll get the answer directly. And T is the absolute temperature. So it must be in Kelvin. In order for that equation to work, you got to use Kelvin. All right, there are a couple of other forms of this. Log of K1 divided by K2 is equal to E sub A over R times 1 over T2 minus 1 over T1. All right, that's also called the Arrhenius equation. And if you take the log of both, let's see, I guess if you just take the log of this, I think that's the one that's on the equation sheet. Double check here. Yes, if you take the log of this, you get this equation. The log of K is equal to a minus E sub A over R times 1 over T plus the log of A. All right. All three of these equations are on the equation sheet. Right there, and right there. And each of them will find usefulness under different circumstances. Okay. The one we'll probably use most often is this one, right? Because normally in problems you're given, you've got 5 variables, and you're normally given 4 of those variables, and then you solve for the 5th one. Right? Oftentimes you'll be given 2 rate constants from which you can solve at 2 different temperatures, so you can solve for the activation energy. And I probably should have passed this out already.
Steve.
Take one, pass it along.
I'll go. That will go back. Both armor. Oof.
Pass it along. If I passed out too many, make sure I get that back, or else I won't have enough for my next section. All right, well, I guess before we actually, so these are example problems that you'll need to be able to work. Before I get to that, I want to make sure I covered everything that I wanted to. One of the things I did want to mention was what that frequency factor is, right? So this thing A, called the frequency factor, is a measure of 2 things, right? One is determined by the number of collisions per second, right? So it takes in that A takes into account how many times things collide. The more times things collide, the higher the rate's going to be, right? So that is directly proportional to the collision rate. But then it also depends on, it's called a steric factor, which simply is a way of saying proper orientation. All right. So in other words, a while back, I think it was back in the 70s, a scientist did a really interesting experiment where they took potassium plus, I think it was methyl iodide. So what they did was they used magnetic fields to orient the molecules, and they shot potassium atoms at this methyl iodide. So you take when they oriented the hydrogens, remember this molecule is a tetrahedron. So you had one side that has three hydrogens in a triangle, and the other side had the iodine. And when they shot the potassium ions at it, right, it turned out that had a different amount that would react compared to when you did it the other way. All right, so in other words, you could orient it like that. All right, so when things collide, not only do they have to collide, but they have to collide at the right orientation. Right? It turns out one of these caused reaction, and the other one didn't. Right? So there's only a certain part of the molecule that when they collide actually results in a reaction. Right? So anybody, you think it's this one, first one, or second one? Second. All right, it turns out it's the first one. What happens is the potassium ion comes in on the hydrogen side and then kicks off, and then the iodine gets kicked off. When it comes here, it just bounces off. Right? So the thing is, if the frequency of collisions is on the order of like 10 to the 10th, right, which is actually what it is per second, it would all depend upon pressures and things. But if only like 1 out of every 1,000 collisions then cause reaction because only there's one little tiny spot that it must hit before it will react, right, then that frequency factor would be that 10 to the 10th times 1 over 1,000, right? So it would be 10 to the 7th, right? So that frequency factor depends upon the probability that they'll collide with the right geometry and the number of collisions that occur. This equation right here, right there, right? What kind of relationship does that look like that is? Anybody look at that and say, oh, that is a blank relationship? Y equals mx plus b. All right, so what that means is that if you make a plot of log k versus 1 over t, you will get a straight line. Sorry. All right, so in other words, what scientists do, and these are experiments I've done. You can go over to the library and look up some of my papers I've published. I've done these experiments, right? So you measure t and you measure k. And then you make a plot of 1 over the log of k versus 1 over t. You get a nice straight line. Okay, so why do scientists measure k's at different temperatures and make these plots? What is that y-intercept equal to right there? Not the number, but I mean, what does that correspond to?
Frequency factor?
The log of the frequency factor, right? So that's equal to log A. So if you make a plot like this, then you can determine for a chemical reaction what the frequency factor is. And if things are in the gas phase, since most collision rates are on the order of 10 to the 10th or so, if that turns out to be something like 10 to the 9th, then that means that 1 out of every 10 collisions collides with the right geometry, right? And then what is the slope equal to? Nope, not equal to K. Yeah, it's minus the activation energy divided by the gas constant. So have that back there. See, here's your variable 1 over t, and so the thing in front of that is the slope. So the fact that you will have some numerical value of the slope allows you to calculate what? The activation energy. You can determine what the barrier that the reaction has to get over in order to react. And in fact, that thing I did right here, that's one that was done in the lab here. It's published over in the library, this molybdenum reaction, if you want to look it up sometime. All right. So let's take a look at these. I think that's everything I needed to talk about. Here we have a couple of rate constants are given. We want to determine the activation energy and frequency factor for this reaction. Okay, very common problem right there. All right, so you got 3 equations to choose from. What do you think would be the best one to use for this particular case where you're given 2 rate constants and the temperatures for each of those? Second one, meaning ln of k1 over k2 equals e sub a over r times 1 over t2 minus 1 over t1. Okay? So we know, so that will become log of k1, and it doesn't matter which one you call k1 as long as you keep the temperature consistent. So 2.23 times 10 to the 5th divided by 1.51 times 10 to the 6th. In fact, all of these examples are ones that were done here at the Naval Academy and published over in the library. What is the rate law? What order of what is the order for this reaction? Second order. That's correct. You can tell that from the units on the rate constants right there. All right, so E sub A is what we don't know. All right, we'd put 8.314 times 10 to the minus 3 kilojoules per Kelvin mole there. And what do I put for the T2? All right, so K2 is there. T2 is there. So what's the temperature for the 1.51 times 10 to the 6th? 250. So I put 250 there.
No.
Okay, what do I put there then?
Kelvin.
Yes, so that would be, what, 523? And the other temperature is 175, so 448. All right, so you can try and do that algebraically, or maybe we ought to just learn how to use the solve function on our calculator now. Does that sound like a good idea?
Yeah.
All right, so you've got a calculator, looks like that. Well, do the best we can. All right, so the solve function is the fourth one, the second over fourth one down, where it says NUM-SOLV. Okay, so you want to hit the blue button second, and then, oops, I got to turn it on first. Second and NUM-SOLV. Second over, fourth down. Okay? Now, I've done a previous problem. Well, you can't see that. So if you have not ever used this, I think it'll just give you an equal sign. So you'll start on the left-hand side. So you'll put log, and if you've already done something, then you can just clear both sides. So I've got a square, and then an equal a square, or I guess a rectangle. Rectangle equals a rectangle. So type in the log, so you hit the log button, and then you need to have, then you put in 2.23 times 10 to the 5th, e to the 5th, divided by 1.51, e to the 6th, and then you put or maybe you don't have to put that parenthesis. Maybe no, I did put a parenthesis and then just went to the other side. Mr. Lee, were you sleeping? All right, you get to Mr. Franshaw. He's got the con. All right, so then we put any type of variable we want. All right, so let's see. Where are the variables? Is it the right, two above the on button. You put an X or whatever thing you want to have. All right, so X divided by, have you done this before, Mr. Lee?
No, sir.
I would recommend that if you have a calculator, follow along here. All right, that has a solve function. Because you're going to need to be able to do this. And probably the first time you do it, you don't want it to be on a quiz. All right. All right, so X divided by, and then I put 8.314 e to the minus 3. And then I'm going to multiply by that thing in the parentheses. So 1 divided by 523 minus 1 divided by, what's that?
Yeah, I just ran out of room, I think.
I've never seen these things run out of room. Now, if it goes off the screen, that doesn't matter. But you can keep typing. 448, parenthesis. Okay, so I don't know if you can see mine, but
It's the like.
okay, so that's what I've put to the very end, and I can scroll over and show you everything that's. See, there's X divided by the 8 point, and so.
Yeah, I mean, I think instead of,
So there's log, and then you put all that stuff in, and then you got the equal sign, and then you put the other stuff in there. All right, it all fits. And then I hit enter. Then you need to put in a value of X. See, the previous problem I did had a value of 808.8897 is the answer. So you'll want to put that back to 0. You want to start at 0 every time. And if it doesn't work with 0, then you got to play with it. But I think any problem I give you, if you put 0 there, then it will converge to the right answer. If you start with something else, it might converge to a wrong answer. Right? So you want to put 0, then you just hit enter, and then it will solve. Okay, so I get a value then. See where it says x equals 49.7. Okay, so that gives me a value of 49.7 for kilojoules per mole.
Oh, okay.
So
Can you make it darker?
X equals to, what is it?
yeah, the x is equal to 49.67, which everything's to 3 significant digits, so you can't carry more than 3 significant digits in your answer. So that's how you use the solve function. I would recommend that you practice enough so that you can do it, because you're going to be using the solve function for a number of problems, particularly in the next chapter. Right? And so, and then in acid-base problems, we have equilibrium problems where you'll want to use your solve function on your calculator. So make sure you can do that. All right, how do I get the frequency factor from this information?
Professor, can you autofocus it again?
Yes. Autofocus or change the light?
Change the...
I guess I want to go the other way.
Thank you.
You're welcome. Okay? So now I need to solve for the frequency factor. Is there some way I can do that? Yeah, we would use the other equation. K is equal to A e to the minus e sub A over RT, and solve for A. A is equal to K divided by, what that was, e to the minus e sub A over RT. All right, so you've got 2 choices. Doesn't matter which one you use. Anybody have a preference? All right, so we'll put 2.23 times 10 to the 5th, molar to the minus 1, second to the minus 1, divided by e to the minus 49.7. And if I put that in, I better use the R value in kilojoules. All right, this is kilojoules, so I have to use 8.314 times 10 to the minus 3 kilojoules per Kelvin mole. That's a very common mistake students make, is they put one in kilojoules and the other in joules, and then you get a very wrong answer. All right, so try to avoid that. All right, and then 175 was 448, or is 448. And so that will give us, and you don't need to use a solve function there. All you got to do is plug that stuff in. All right, 2.23. I mean, although you could use a solve function, but there's really no point in that. So I got to get out of that. Got to quit. 2.3 e to the 5th divided by. So, and if you decide not to use a solve function on that, you obviously can solve for it algebraically. There's no problem with saying e sub A is equal to 1 over R R times. That's when you start making mistakes. We're going to do all that. Divided by the whole thing of 1 over T2 minus 1 over T1. You can do that. But you won't be able to do that in the next chapter when you try and do equilibrium problems. I will be very impressed if anybody can solve like the x to the 5th power problems we're going to have to be able to do in the next, we don't do quadratics, we don't do quartics, and so we actually get like x to the 7th plus, x to the, something times x to the 6th, and you're going to need the solve function to be able to do that. All right, divided by e to the minus 7 divided by 4 e to the minus 3 by 448. 1.39 times 10 to the 11th. That's what I got. And that's molar to the minus 1, seconds to the minus 1. Frequency factor has the same units as the rate constant.
So it could vary.
Pardon me?
It could vary depending on the reaction.
Yeah, if it's a first order reaction, then it would just be seconds to the minus 1. For a third order, then it would be molar to the minus 2, seconds to the minus 1. So whatever the units on the K are, that's the units of the frequency factor. All right. What about that one? Hafnium plus carbon dioxide goes to form hafnium oxide plus carbon monoxide. You're given 2 Ks. You want to calculate a rate constant at a different K. How do you do that?
You didn't finish one.
Pardon me?
You didn't finish one.
Oh, we didn't? Oh, we didn't. Man, there's 3 questions to it. All right, maybe we don't need to do the next one then. Although, there are now 2 ways to do what is the rate constant. So, what is the rate constant at 25 degrees? Let's do it the easy way. A e to the minus e sub a over RT. All right, so we would put 1.39 times 10 to the 11th e to the minus 49.7 divided by 8.314 times 10 to the minus 3 and 298 now. All right, so all I'm doing is I'm plugging in the numbers for the frequency factor, the activation energy, and the gas constant with the new temperature. So times e to the minus 49.7 divided by 8.314 e to the minus 3 divided by 298. Do we expect that to be greater or less than the other K's? Syntax error. Great. See what I did. All right. Oh, what the? Oh, I used a subtraction sign instead of a minus sign. All right. Anybody get a number?
3.36 times 10 to the 11.
And 2.7 times 10 to the 2.
Well, okay.
Okay, yeah. I got 2.70 times 10 to the 2.
That's what I got too.
Molarity to the minus 1, seconds to the minus 1. All right. How would you do this one? I mean, we could do it the long way, or we could do it in 2 steps, right? How did we end up getting this one? How many steps did it take us to do this one? 3 steps. We first had to calculate the activation energy, then we had to calculate the frequency factor, and then we could calculate the rate constant. Is there a way to skip one of those steps? The answer is yes. You'd start with log K1 divided by K2 equals E sub A over R, 1 over T2 minus 1 over T1. All right, now, you've already done a problem like this, and so when you go onto the calculator, all you have to do is edit it. You just have to put in the new K's and the new T's, and then, when you pull that up, your old problem will show up. And you did one just like that. So all I've got to do, let's see if I can show you. All right, so now you've got the problem in front of you, so you can see. So there's my old problem that I did. So I can now change this to 7 point. Let's see. I think we wanted. Well, I guess it doesn't matter. We can just say 7.23. 7.23 times 10 to the 7th. And then the next one is 1.14 times 10 to the 9th. Okay, and then go to the other side, and I need to put the right temperatures in there. Right? So I think I'm using the lower temperature for, let's see, I did this one, the lower temperature for that. So did I just do that? I put the higher temperature there. Okay, so that's 290. This one, okay, so that's 225. So that is 498. So I'm going to put 498 there. And then I put 298 there. Now, if I mix those temperatures up, I still get the right activation energy, only it'd give me a negative activation energy. Activation energies are always positive, right? So if you mix up the, let's see, I'm going to then go back here and put it back to 0. And, all right, so I had them right. So the activation energy is equal to 17.0. Okay? And so now I want it at 350. So all I have to do is set up the new equation where I leave the K1 as the variable and put in what the activation energy is and put in the two temperatures and one of those K1s. All right, so let's use normally what we want to do is the one that's closest to the temperature you're looking for. I mean, it's not going to matter because these are perfect. Yes. Oh, yes. Okay.
I would never know there were words there.
Okay, so what we're going to do now is use this exact same equation, only we know what the activation energy is, and so we're going to solve for what K1 is. So I'll go back. Let's see, I need to quit. Quit, and then go back into that number solve there. And now I'm going to make the first K as a variable. Okay, so I'm going to make that the X. So K1 is the X. And I'm going to use still K2 is the 1.14 e to the 9th. Now I got to put in the value of the activation energy, which is 17. So that's 1. Okay, now I got to insert it. So I can insert 7. And it's 17.0, so I can just leave it as 17. And then put the temperature that I need right there. All right, so the temperature I'm looking for is 350. So that's what, 523?
623.
Oh, 623, yes, you are correct. 623. Okay, and so that then should solve, and I'm going to put a 0 there. That should solve for the rate constant K. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2.60 times 10 to the 9th. Molar to the -1, seconds to the -1. I guess you can't see all that, right? What's wrong with it? All right, so I just edited that equation to put a K, to solve for the K instead of the activation energy. So I can do that all in the calculator. All right, last thing we'll do here.
Professor, what was the answer to the last question?
I got 2.60 times 10 to the 9th. Did anybody get something different? Now, I would always make a does it make sense check. All right? Does that make sense?
Yes.
Yes, because it is a higher temperature and now is higher than the K of the lower temperature. Right? So at least, and it's on the same order of magnitude. Right? So if I've got something like 10 to the 23rd there, I would say maybe I better go check my work. So it's always a good idea to look at an answer and make sure it makes sense.
There you go.
All right. Here is the plot for ytterbium with N2O, and it's a plot of log K versus 1 over T. You can go over to the library and look this plot up somewhere. What is the activation energy and the frequency factor? If you're given a plot like that. Okay, remember, we've got this equation, log K is equal to minus E sub A over R times 1 over T plus the log of A. So this has a formula Y equals mx plus B. So if I want to get the activation energy, this thing right there is equal to the slope. So it's minus the slope times R. So the slope is minus 2.5. And what are the units on that? Rise over run. Anybody figure out what the units on the slope would be?
Natural log of Kelvin over L.
Actually, these are unitless over here. When you have a log thing, right, then that's going to...
Kelvin.
Okay, so it's rise over run. So this is 1 over Kelvin. So 1 over Kelvin gives Kelvin. And the gas constant, 8.314 times 10 to the minus 3 kilojoules per Kelvin mole. So that will give us what our value of the activation energy is for that one.
Wait, why do you multiply that?
You had multiply by
I thought that, yeah, you're right. There is a negative sign in front of that. So minus the slope times R. So since that is equal to minus the minus. So anytime you get a negative activation energy, you know you've made a mistake. You don't get negative activation energy. So 2.5 times e to the minus 3 gives me a 20.3. And you'd have to know actually what the data that was used to make this plot is in order to get how many significant digits are justified. But I know from doing the experiment, you get no more than 3, right? So that would be 20.3. All right. So let's make sure we've covered everything we're supposed to do today.
We didn't do the second part of that one.
Yeah.
Oh, the A. All right. You are correct. I also want the A. What is A equal to? Almost. E to the y-intercept. E to the 25.788. Because the y-intercept is equal to log of A. So if you want A, you have to take E to that.
That's a big number.
Well, yeah, that's not unusual for these type of chemical reactions.
1.58 E11.
1.58 times 10 to the 11th. Okay. So units of molar to the minus 1, seconds to the minus 1. I just happen, oh yeah, there it is. It says in units of molar to the minus 1 seconds to the minus 1. All right. So make sure we've covered everything we need to. Use collision theory to explain how reactions occur at the molecular level and explain the concept of activation energy, how it relates to the variation of reaction rate with temperature. All right, so that activation energy is the barrier, and it is related mathematically by the Arrhenius equation. Right, we can do calculations involving activation energies and rates using the Arrhenius equation. Be able to interpret potential energy profiles, use them to determine the activation energy and potential energy changes for a reaction. We talked about that. Be able to use the Arrhenius equation to calculate rate constants, activation energy, and frequency factor. All right. So we'll cover the last few learning objectives on Tuesday, because now we need to take the quiz. So, do that. Sure you